intro, we're very happy to greet Anna Radovanovic. She got her PhD from Columbia and she's now working at Google. She used to work at IBM. And Anna has a fascinating, extremely diverse background, both technical and business problems, and being able to bring everything of that together. So without further introduction, thank you.
So hello everyone. I actually thought about giving a broad story initially, but then I thought, okay, I will give a story about the actual project and how we came up with probably, as far as I know, to the best of our knowledge, state-of-the-art solution that we turned out to show that it works in practice. And and all this story started as when I moved to the project, from New York to California. Actually, there were people who came and got interested into energy, and I never worked in this field. And so I worked in different areas of stochastic optimization and distributed optimization. This is how I know Stephen Boyd. But then there was this team, and they offered, they said, okay, let's revolutionize and optimize the energy consumption, energy distribution. And it doesn't have to be any grid, some particular energy system describing the grid in the United States. There are energy systems on the island in Africa, I mean non-existent ones, where you want to connect two villages, and one village has a wind power, the other village doesn't have any infrastructure, and you want to build ad hoc energy systems. So how would you optimize these? How would you think of a mechanism to actually formulate the optimization problem that is flexible enough to capture a general energy system? So with general generation sources, because now we have wind sources, we have ad hoc, we have actually utilities as well, right, in established and some parts, most of the parts of the world, but also we have all kinds of loads that are coming up, right? It's not just that we have old loads, but we have, or actually network infrastructure that demands power, but we have thermal and generally differable loads, large loads like EVs that you can also control in real time, hopefully, and optimize the energy because I'm cost objective. So I'm going to formulate this. So I will show you how we approach the problem. So, and okay, this is, let me just before then mentioning, because there were some groups already when I got into this area. Seriously, I just start from scratch and then I read literature and say, okay, what exists, right? What does it exist in the academic world? So I ran across some of the work from Caltech group, I'm not mentioned, but Javad Lavaye, and there were a lot of Steve Law and others who actually had a way to solve these energy optimization problems. Then there was an attempt from Stanford University teams to actually, and Raj is among them, to come up with formulation in some probably simplified method that we couldn't use. So when I started working on that, they said this is great, but we have to actually apply it to real size system because we have to try it on real hardware. So let's come up with a formulation that is going to run on real hardware, and let's come up with a formulation which is going to be able to, where we are going to be able to prove it that works in these traditional frameworks that Java Caltech teams and Columbia teams and ETH teams like Marina, they are also trying a lot of concepts works. So we want something general. So this is how it started. The remote should work. Doesn't matter. I don't know. This is the right one, right?
I think is the power turned on? The thing doesn't have focus. It's focusing on the.
Oh, I see now. Let me show you.
So there is.
I see what it is. Look. You see the. It's now it'll work.
Okay. Okay. Cool. So this was a brief introduction, and I will really give the formal actually description of the problem, formal representation. I will not use epsilon, but I will say small enough, okay, instead of that. And because I did care when we came up with this approach to actually and to show that it works probably so what we observed, the general power distribution system with different types of loads, generation, storage, and transmission. So completely different, and we want to efficiently allocate power under various operational constraints on voltages, power flows, thermal dissipation along the power lines, bus powers, and all sorts, ramp-up rates of generators in general, and so. So we have a very general energy system. So this system, maybe if you observed, you always have devices, whatever these devices are, I just mentioned, they are connected to the network. So they are connected via these terminals, and the devices sharing a single line with a common voltage, they are called buses. So they are actually attached, and this single line that connects devices are buses, while buses are connected via two-port devices that are called transmission lines. So this is the concept. So we have a set of terminals, a set of buses, which is basically a partition of set of terminals. Okay, so we want a general system, so not a DC, but general smart AC system. So everything is represented through a complex variables, like we want complex voltage, current, and apparent power, right? And our cost functions can be operational cost, can be, you mentioned, ask a question, opportunity cost of producing, having a storage, and buying a storage to use it in the system. And our assumption here is that these costs are nonlinear in general, but they are convex. If they're not truly convex, because you can see there are some studies saying that the operating cost of a generator has some discontinuities. Yes, okay, we use convex relaxation, some approximation of that cost function. Okay, so what is the optimal power flow problem? It's so old. Everybody, so many electrical engineers tried to address this problem, and I just listed a bunch of things. So we can say that we minimize the sum. This is our cost. It can be economic cost, any kind of, right? So it's a sum of this convex function across, and they correspond each. It's a sum. It's kind of a separable function across these convex functions of terminals. And then we have, what do we have here? We have what is the apparent relation between the apparent power, voltage, and current. We have the consistency, the fact that all terminals, that are all devices that are connected to a single bus, they have the same voltage. They must have, we have Kirchhoff's laws that need to hold. We need to know that if you have a two-port device transmission line, that the input current needs to be equal to the output, so you have to respect the sign convention. Usually in this system there are a lot of papers about this voltage regulation. So you don't want voltage to vary too much from some nominal values, so we have bounds on voltage and how much it can vary. And also the important constraints are also these ones, which is that the transmitted power, or the total power that you input into a transmission line, needs to be bounded, its norm. So, and apart from that, there are many other possible constraints, right, that I'm not listing. But you see this problem immediately, even if these functions are convex, and there are a bunch of here inequality constraints, that's fine. There is this first constraint which says that makes the problem completely non-convex. And the feasibility region of such problem is very discontinuous. The problem in some work that exists was shown to be MP hard. And what also we noticed when we read these papers, we saw that, you know, the grid was described through a bunch of a matrix of admittances. So how are we going to estimate these admittances when they change, if they change due to thermal dynamics or anything? How are we going to just, you know, running this and describing a device just through this matrix of admittances seemed to be totally infeasible, really. So maybe in some cases we will know what is the resistance or admittance of a device, but in some cases we are not going to be able. Also, sometimes you will need to capture the ramp-up rates of a generator if you want to capture some dynamics, and the traditional solutions did not address this problem. So this is what we started working on. And it seemed to kind of, so we needed to kind of reformulate the problem first to see whether we can do something about it. And first we said, okay, is there some convex relaxation that can be a decent one, for which we can show that it's a decent convex relaxation, we can be close to the true optimum of this very truly non-convex problem. And what we did, the fact that these voltages cannot vary too much, voltages on buses, and usually that in most cases it's a reality, phase differences between the end of the ports of transmission lines are not large. Well, why not then express the voltage complex voltage expressed through this phasor, take a phasor representation of voltage and replace it in all these equations. And use this, the fact that these things are small, actually phase differences and voltages, use this fact to come up with the approximations of these sorts. So that was the major trick, honestly, like to come up with, use just this approximation to replace current, because current and voltage are connected through this simple Ohm's law, general Ohm's law, and then just reformulate the problem. And so then this is what we did. So we came up with an approximation of the optimal power problem, and we were shooting to have linear equality constraints and convex objectives and constraints, right? So we could have just convex, this quadratic sort of, or convex inequalities, right? And this is what I wanted to just give you an example what are the sorts of loads we can capture. And this is just a subset. These are in this first draft, but I will talk about extensions because we capture all sorts of loads in storage. So for example, we can capture, these are the constraints, like if it's a constant load drawing a constant power, then we can do just simple inequality. If it's a power factor imposed on some, if you have a generation with some power factor constraints, it's easy inequality constraint. If you have a curtailable load like dimmable lights, yes, why not? We can like model it as some hinge function, right? So if you have an impedance load, then you can write this equation. Then also, so when you do this, you see this is inequality, again, a non-convex constraint. Well, in order to do that, we come up with a convex approximation. So whenever, for what we do, for this active power, what we do, we replace equality with inequality, and then we approximate the exponential by doing quadrant approximations around some operating point. So just quadratic approximation around the operating system, operating point of the exponential function. And for reactive, I said, okay, it turns out that, and there is a strong reason for that, you don't need to actually necessarily use quadratic approximation. We can just do linear approximation and put equality. So instead of basically having exponent here, we just have this now approximation. So, and this is what we keep doing, and also I have to admit the power lines are the horrible parts, right? This is the worst thing. So power lines is this is giving trouble in general. So this is how we use the same logic. So active power losses we basically use, instead of having equality and something of this is, I call this a loss function, this norm of the difference of complex voltages in the end of transmission lines. We just use this quadratic approximation for power loss and linear approximations for power flows, reactive, active power flows through the lines. So this is just approximation on all those non-convex constraints, using after replacing the phase representation of the voltage. So what here in this, when I do convex approximation, as I said, I do it around the current operating point. So, and then we tried doing this because it's so simple now. It converges in so quickly. It's a convex. So can we have something provable that if we keep repeating doing this, that we converge to the actually optimal solution of the original problem? And I can tell you, if you see this paper, even though those, I couldn't even understand when the original and all published research is going to give the global optimal. It's not clear. It was shown that in the case of 3 networks, you have probably, you're going to get, even if solving the SDP will give you the optimal solution. But for mesh networks, there was no way. So we wanted to see if we converge by doing this. Do we converge to a global optimum? Do we converge to a local? How far, how often that happens? And we wanted to actually prove something and show how it works on mesh networks, mesh transmission and distribution networks. And this is what we did actually. So now it's simple, right? You start from some feasible pair of phasors and these voltage angles and these variations, like this small v and theta, and then you keep solving the problem. And whenever you solve, you come up with a new solution, becomes the operating point in the next iteration. So you see, this is a sequence of convex optimization problems, and what we show that and I have to repeat again, we had to assume this small variation, which is very realistic assumption in the system. No one wants, like for example, if the nominal voltage on the bus is 240 volts, no one wants it to be below 180. So everyone wants this small variation to be. So as you can notice, and which I just raised as a point, there are no conditions on network topology. It's just a general network. And we show that for small variations of this sort, this algorithm is probably converging. So if you say, okay, so I mentioned that if you read some of this literature, how it compares to this is how we got connected and started working with Steven and his actually PhD students, because they had a version of the paper where they do not address basically these voltage variations and phase angles, and this is pure extension of the traditional work, of that work too, in particular. So, and also I just wanted to say, so this, whatever I'm describing, I will just I'm going to state 2 results that we show, and I will just give you intuition why that works without proving anything. But I just want to say, listen, so now I didn't put storage constraints, but everything can be extended to a time horizon with storage and storage dynamics. You can put thermal loads, like refrigeration. You just have to learn parameters, like, right? It's not just, but you have to have some thermal dynamics put as a constraint to this problem. But everything is feasible now by doing this, in this approach. So the main results are basically that if you do this relaxation in each step, it's not that you're solving, even though you relax and you have inequality constraints, it turns out to be tight relaxation, and the solution is that you're going to have equality. So this is the first. So those inequalities, the optimal solution in each iteration is gives the tight constraint, and the second result is probably the one that took us the longest to prove. It's a local convergence, but this local convergence is basically strongly relies on tightness, and the assumption of tightness, the tightness is based on the fact that we say positive LMPs. I'll just describe whether it's realistic or not. This is locational marginal price in the system. So if you add more load to the system, if the assumption is the following: if you add more load to the system, if if the cost grows, operating cost grows or power cost grows, then we have a tightness in each iteration of this convex procedure. Iterative procedure, which is the case in all like normal case, right? Sound scenarios. And the second result is just strongly relies on that, and the result one, and strongly relies on the convexity, right? Because it allows us to prove this uniqueness of the solution. So I'll just not go in details, but the whole step, basically the convergence relies on the fact that these cost functions are convex, but even if they're convex, there is this quadratic approximation that helps it converge. It's kind of regularizing the search or the steps towards the optimal solution. So the first thing we had to show is basically that the loss function, I'm missing here square, is actually locally convex. And then to use basically probably very standard techniques, but I show mainly rely on exploiting the Kuhn-Tucker conditions of optimality and the tightness in each constraint. But what we show also, what is nice about is that it's locally converging, and it's not only converging, but it's a quadratic rate of convergence. So we get exactly the rate of convergence of this algorithm. So after this, so the great justification that we are doing something right is to test this on examples where everybody fights, over. So in the literature you have papers that says, okay, my method finds the global optimum on these loop networks or these mesh networks. So everybody says, okay, this method didn't find it in this many, converges to local solutions. So we put a lot of examples from these papers and tested our iterative approach. And these are the results where most of the methods fail, okay? So basically, we find the global minimum everywhere except in this case of this network, and I will show. It's not important, but why? Because the phase angle constraint was not small enough, tight. So it found another local minimum, not a global one. But optimality gap was, does it matter in practice if you're in small enough region, but not small enough to be even some minimum, like if it's a convex function, you shouldn't, and continuous function, you shouldn't deviate that much in the value of cost, really. So that is an intuition that we were not worried too much. So if we when we constrain this phase angle difference more, we actually converge to the optimum.
Is there some, could you go back to the previous slide?
Yes, yes.
Is there some rhyme or reason to how these networks get chosen as the test networks? Not for you, but just...
In general, I didn't know any of this, but there is this Smart Power software, and they get these are actual grids. These are actual grids, pieces of the United States grid, right? Transmission systems or distribution. This, I think, is an example, this is a typical school example. Okay, let's try what happens in the case of loop. But these three, these are the actual meshes that come as real examples.
So they're ad hoc, but there's been no effort to extract characteristics that are relevant to
They are not ad hoc. These three networks are real networks.
What I mean is that the choice of them are ad hoc. You look and see what's out there, you just click them out, but you don't try to organize them in some sort of intellectual framework.
No, I did not.
Not you.
I know, yes. For me, we selected examples to see where different approaches differ a lot in their results, and we wanted to see how we perform. Yes, so that was our criteria. Yeah, you're welcome. Yeah.
just to help about the 39 plus network. If I can help.
Of course, of course, of course.
In PES society, Power Energy Society, they have some classic tests. And those systems are supposed to be very hard to have solution. They used to say the following: if you are propose work on that system, you can be sure that it is a good one.
Yeah, okay, so that leaves me unmoved unless it's in a already in a structure. So, okay.
They say that.
I'll accept, right? No, when you did that.
This sounds ad hoc, yes. Yeah.
So
This
sorry.
sounds ad
So
hoc.
thank you.
So, yes, so these are some plots that we wanted to show how fast this, if someone says, oh, but you're showing so many Convex programs, but it's not really the case because it converges very fast. Very fast. It's enough actually to run usually 5 iterations to be good enough. So now what did we do? Now we came up, I don't have any more slides, but I realized that maybe it's just now it resembles an academic talk. No, I mean, because I still am trying to prove that I can do research probably, but then what we did, we actually had some hardware examples and devices, and we put some intelligence and made them talk. And you see, we made them because you say, who is going to solve this centralized problem? Well, we don't want to solve it centrally. We can just use some consensus algorithms. And so, because if you remember, the objective function was separable across devices, so why not use consensus and do messaging, just simple messaging. And what is nice, because these devices don't even need to reveal their information. They can have their own cost functions, they can have their operational constraints, and they can hide them away from anyone else. No sharing, which is the way to do if you have also privacy issues are important in this system, as it was mentioned in the first talk. And it was nice because we showed this, that this is convergent to the global optimum. We did this, we applied, we have even transmission line in our lab, and 2 ports were talking to each other, which was impressive. What is another thing now, you have communication issues because all of this relies on the fact that the algorithm is going to work perfectly well. So these devices were talking, but an intriguing stuff is that yes, now everybody first running the optimization, let's say it's fast enough locally, but then they're sending to the runs are different depending on the device. More complicated device it is, the running of a local optimization is good to be longer. So we have asynchronous messaging between these devices, so that we need to see how these consensus algorithms perform in the presence of this asynchronous messaging. Are they going to converge? I mean, also, what we noticed that when they're exchanging, we tried many ways of communicating. We had communication channels like Wi-Fi channels, but also we had power line communications, trying out to see what is the loss rate of packets that are exchanged. So there were a lot. It was probably the best time in the project that you come to try the algorithms and you actually see that it's quite robust to certain things and it's not. Like, for example, we noticed that this consensus messaging was robust to asynchronicity in communications. It was robust to losses, packet losses. In power lines, not obviously. You cannot. There is some. We didn't. It was. We tried to actually analyze it to come up with the problem is extremely hard. Extremely hard. What is the threshold in this power loss, above which we are going to ensure that we can ensure the convergence of consensus algorithms? But it was terribly. For us, at that time, we couldn't actually. We could just experimentally try this. Things, not prove. So what is nice also, because we have cloud, and like everyone else, and distributed computing platforms running this optimization or having homes attached to this local optimization solver, local optimizations can be extremely, it's a possible thing to do. So hopefully one day one of these things are going to run somewhere in real, but for now it's just an exploration, and it was a great exercise for us. Thank you.
Questions?
Yes.
So what's the application of this algorithm? So let's say from control perspective, there's some users who want to minimize their payments. So in your problem is minimize the total payment. So how can we utilize this your algorithm to solve the problem?
So you're asking me what is the cost actually structure? What is the actual cost in the objective function? So for example, for us, how we thought it's an operational cost of these devices. For storage is the opportunity cost when you buy storage and implement it. And also there is a cost of charging and discharging because batteries lose their efficiency a lot, like through time and capacity. This is for battery storage cost. Then for devices like generators, generation cost, there are some we found in the literature and people who examined it previously, the generation cost is actually in relation to this, in a quadratic relation to the power that they generate. And what we try to do is to minimize the social or to actually maximize the social welfare or minimize the social cost. This is what it means. By running this consensus algorithm, we were getting these duals all the time. These are duals associated with the power flows, right? And these duals, we could see that when you get a new load attached, it's like higher demand. We could see how the duals change, that the price change depending on what is the price of generation and how much load is in the system. So we could track, so this is, I'm not saying we didn't analyze the efficiency of this mechanism, pricing mechanism. We didn't pose the game theoretic problem. We didn't see, okay, if there is equilibrium or this optimal solution, is it an equilibrium? Okay, this pricing mechanism and picking prices just by taking the duals of this flow constraints. And I talked to some people who do that, but we kind of haven't had time to get deep into this. Yes, does it answer your question?
So basically the question is, as a user,
okay.
So I can change the power, how much power I consume.
Mm-hmm.
I can change how much I pay, right?
Yes.
And you have another power, voltage. How do I change the voltage?
You don't need to change voltage. You can put just power constraint for those that matter power. So voltage is just for a bus constraint. So you will have resistive loads that we describe as resistive loads. But you have just constant power loads that we describe as a power load. So for a user so you do not have to put voltage everywhere. You just put, like for example, battery. We are not going to put a battery, but we are going to put an equation that relates the current state of the battery, its efficiency, the previous state, and how much you charge it or discharge it. Right, this is the beauty of this approach because it's kind of flexible. You describe the device in the way you want. It's convenient for that device. It's suitable for that device. So, right, so it will come up. It will not violate any of these constraints. I mean, if it's possible not to violate, right? If you come up with a feasible formulation in general, right?
Another question basically is from communication perspective. I remember Wu Chang has a paper on this network utility maximization. So intercongestion control problem can be formulated as minimize the cost, the total, or maximize the total utility. It's also the cost function per device is a convex function. So in terms of the cost function, it's similar to your formula. Also, we have a network, communication network.
Yeah.
But the constraint is quite different. Constraint is very simple, just linear capacity constraint.
I'm sure costs are, I mean, cost structure can be anything really, right? So we try to put it in the framework of energy, what matters in this energy world.
Is there any relationship between those approach, network retrieval manipulation, to this approach?
I didn't see. And actually, as you saw, the whole point in this optimization or the approach is not, we are not relying on the structure of the cost function as long as it's convex. We don't care. And it's separable, really. Even doesn't have to be even separable unless you want to solve it in a distributed fashion. But what we just basically are trying to find a way to deal with these non-convex constraints.
That's a good thing to point out. Is some people, some grid operators, RTOs, RSOs, having efficient solutions to this problem see big strong some folks. They just for a lot of reasons, both economic and political. So you have the wrong solution and they get sued.
Yes, but I talked to some people who actually come out from these Caltech research groups that worked on the OPF for some time, and they have a problem, for example, that they have to estimate this admittance matrix. Says, okay, so we are getting completely wrong solutions. Javad, actually, because he claims that I talked to Javad too, he probably made the most of the progress. He's at Columbia in solving these OPFs, and he's using the SDP approach in solving it. He made a lot of progress. So in order to solve SDPs, when I saw SDPs first, I thought, okay, maybe I should implement this, and I realized how hard it would be and how non-scalable it would be in real life to just, and you need to solve it centrally, right? So, but Javad came up with the ways to actually really optimize the processing or solving these SDPs. So he made a huge progress in that space just to make SDPs work. But again, I think the approach is not maybe flexible when you have such a variety of different devices with different constraints. Yeah, you're welcome.
Just in comparison to network flow, I mean, it seems like a key element here is the complex nature of the function, right? I mean, so you're using the logarithmic mapping.
Exactly.
That's a key
That
you might not have in network flow. I mean, a communication network flow where everything is really just a scale.
Yes, everything is a scalar in flows, right?
Yeah,
yes.
Yeah. So that's a key. There might be other applications.
Maybe. And here you cannot relax these powerful physical laws, right? So just like it's not going to.
Quick clarification question. You said the original problem is non-convex. So how do you get the global minimum?
We prove that it's converging to a global minimum. We are never solving this original problem. We are coming up with relaxation, and through sequence of iterations, iterative steps, we show that we converge to that one.
It's a local convergence.
It's a local convergence. Yes, so it's a local convergence.
His question is, you say if you can prove you converge to the, to the minimum or whatever, but it's of your relaxed problem, not of the original problem.
No, we prove that we show to the convergence to not to the original problem. That's the result. I don't know whether I stated it properly, sorry.
Well, and you have no idea what the gap is, presumably.
Okay, so how about, maybe I should reformulate the result differently, but it locally converges. So I say if the variations are small, then small enough, then it's a global optimum, okay? And if it's not, you can use the continuity of these psi functions to say that you're the order of, right, these variations squared. So that's the result we can show. So
the epsilon came out.
It's epsilon is from there, yes. Any more questions?